I will wait for a few more minutes and then we'll start 5 minutes. Then we'll start. Okay, I think you can start. By the way, if anyone wants, you can record this. So let me know when you are ready to record. Is anyone going to record? Okay, are you ready? All right. So today we are going to continue with Verilog syntax, and we're going to learn by example. And we're going to discuss about some combinational logic module and how we can model. So this is just some description. Now here we have an example that shows the use of if else, just like C++ programming. We can also use if else for Verilog program. On top of that, uh, we have already learned the design flow model and the structure model. So today we are also going to learn the behavioral model. Behavioral model is just the name says uh, is what is the behavior, what is the property of that of a block or a site. Data flow modeling represents the Boolean function. Structural modeling represents circuit diagram, and behavioral modeling is a description that which means if I do this, then that something will happen. If I don't do this, something will not happen. Something similar to that concept. It's just a description. It's not Boolean function. It's not schematic diagram. It is a description. So in this, this is a 2 to 1 marks. We have input A, input B, and we also have a selection P. We have only one selection pin that is connected with N2, and selection selection bar or S bar will be connected with N1. This is our uh, 2 to 1 marks, and output will be the logic diagram will be A and S bar or A and B and S. Okay. Now we can model it in terms of circuit diagram also because we have we have this schematic. So I can do the circuit diagram. We also have the Boolean function. Can also do it in terms of data flow modeling. However, we already learned structural modeling and data flow modeling. We're going to learn behavioral modeling. Module is the keyword. Module name, uh, input output port. The input output ports will be A, B, S, and Z. However, I don't know which one is input and which one is output. This is written in 95 version, Verilog 95 version. So we can write, now we have to specify which one is input and which one is output. Inputs will be A, B, and S, and all are 1 bit. Output will be Z. Now here is one. Another line, we know that register is the memory. So we have to specify the memory. And why do we need to specify the memory? Because this is a pass transistor. I don't know, you have already learned about pass transistor or not. For pass transistor, we can disconnect the input and output. If we have a combinational logic or a AND gate or gate, as long as we have input, we will have output. Or there must be some input, there must be some output. Okay, and there it will be direct connection. Let me give you an example. Hmm. Okay, here's the AND. Now for the AND gate, A must be either 1 or 0, B would be 1 or 0, nothing else. And once we have the input, output is directly connected. Based on the inputs, output will be something. But for pass transistor, it works a little bit differently. You can think about as a water tap. If we turn on the water tap, then input will be connected to the output. But if we turn it off, then input and output will be disconnected. So this is one special property of pass transistor. We can disconnect input and output. However, for the AND gate, CMOS AND gate, we cannot disconnect. It must be one of the two value, 0 or 1. And depending on that 0 and 1, it will be output will be whatever the output comes out, whatever the result comes out. So there is input and output are always connected. However, for pass transistor, input we can disconnect input and output. Okay. Okay. So here is the CMOS AND gate or NAND gate. Ah, look, here's one. I said and NAND gate, NAND gate. If you notice, the input is given for the CMOS input is applied at the gate of the transistor, and output is taken from the drain of the transistor. So here is the basic difference. Input is provided at the gate of the transistor, output is taken at the drain for the CMOS. For pass transistor, input is provided at the source and output is taken at the drain. So this is the fundamental difference, and as a result, we can cut off or we can disconnect the input and output of the pass transistor. Uh, I'm not sure whether you learned it in 283, but at least I'm sure uh, Dr. Tisha will provide you a lot more details in terms of circuit operation and etc. However, this is the basic concept for fast transistor and CMOS transistor. Okay. So why am I explaining? Because if I disconnect, an input and output, what will be the output? We must have some output, right? This node must have some voltage. So as a result, that's why must have. So when I say must have, that is no condition, connected or disconnected, does not matter. It must have output. So if it is disconnected, what output should we expect? The output that was at this node previously. So when I say previously and now, it means there is a time factor. And when we have a node as a time factor, with a time factor, that node is called memory node. Make sense? Okay. So this node, we have to identify this node as a memory node. When we identify something as memory, then we declare it as the register. All right. So whenever you see fast transistor, output node, you have to declare the output node as a resistor. Otherwise, it cannot hold the value. Why do we need to hold the value? Because if it is disconnected, then I don't know what is the result. It will become unknown immediately. That's why if a bus transistor is disconnected, so that we can hold the value, and then that's why we need to use it as a memory, or you need to declare it as a memory. And in order to declare a memory, we need to use the keyword register. Hopefully it makes sense. Now, we're going to describe the behavioral model for the first time. This is the structure of the behavioral model. The data flow model is assigned, then Boolean function. The structural model will be connectivity and or etc. Or sometimes we can use built-in function, or we can use our own function for the structural model. For the behavioral model, this is the structure. It starts with always. This is the keyword. When we say always, that means it will give behavior model. Each model is identified by different keywords, assign, and then logic gate for an internal or built-in or user-defined function for a structural model, and always will be used for behavioral model. And then we have to use the add sign, always add. And this is fixed, always add is fixed. Then inside the bracket or parenthesis, we need to mention the signals, the input signals. We need to mention the input signals. This is kind of very important. The input signals, or the list of input signals, very important. Why? Because if I do not include the list of input signal in this within this parenthesis, it will ignore that signal. Other way to say, we have A input signals, A, B, and S. These are the input. Don't worry about the output. We're going to talk about output later. Input signal, A, B, and S. I have to mention all three signals. Otherwise, this function will not work. So if I write only A or B, then S will be ignored. And if S is ignored, then this function will not, and that means this S signal will be ignored. If S signal is ignored, that means this 2 to 1 marks will not operate properly. So that is why I'm not saying that we have to include all the input signal. We have to include the necessary input signal, not all necessary. But most of the case, it will be all. Sometimes, if we have many blocks, multiple blocks, we do not need to include all the signals. Okay, but we have to include the necessary signal because inside this always we have S, we have A, we have B input. If anyone is ignored uh, within this bracket, it will not operate properly. So this list is called the sensitivity list. Sensitivity list. That means if any of the signal is changed, then it will operate. This function will or uh, if any of the signal is changed, then this logic will run or operate. So how it works? If we have a 2 to 1 mass and it is sitting there, so it will all continuously check, always check. It will continuously check. Suddenly, signal A is changed. Then what will happen? Uh, because it is changed, it will operate if else logic. If is equal to 0, then Z will be equal to A, or if is S equal to 1, then Z will be equal to B. So how does it work? If S equal to 1, output will be B. S equal to 0, output will be S equal to 0, output will be A.
স্যার এই পার্টটা আরেকবার বলা যাবে? আউটপুট
কোন
আর
part?
এসের পার্টটা কেবল যেটা বললেন।
Okay. So let me. I always try to provide parallel examples. I'm sure everyone is familiar with C++. So let me write it code for C++. Say S equal to 0. So what will happen? It's a while loop, right? I think there will be end or something like that. Anyway, so it will continuously check while. Suddenly S will become 0. Then it will go inside this logic and do the if and else, if and else. So similar to that, always or while, right? Always means all the time, and while is also all the time. While it is checked, and it will check. Uh, I just provided a simple example, yes, but I can also add is um, and a or b, something like this. So if it is true, then if else will operate. So here is the same thing. Always it will check. It will keep checking always, and suddenly there is some change. A or B or S shape will change. If it changes, then it will go inside this logic, if logic. If S is equal to 0, S is equal to 0. If S equal to 0, what is S bar?
1.
Right, 1. Then output will be A. Why is that? If we apply signal 1 at the gate, transistor on or off?
Transistor is on.
PMOSে ওয়ান
Okay.
দিলে
Mhm.
PMOSে ওয়ান দিলে অফ হয়ে যায় না?
So is it PMOS? Is it PMOS?
স্যার বুঝতেছি।
ইনমস
Is it PMOS?
হ্যাঁ এটা তো সিমস
So CMOS, how can we make CMOS?
পিমস আর এনমস এর কম্বাইন করে
Right. So do we see any NMOS or do we see any PMOS? Which one is NMOS and which one is PMOS?
So both are NMOS.
Right. So both are NMOS. So that means this is not CMOS. CMOS, we will need NMOS and PMOS for CMOS. So many MOS. But pass transistor, here we have NMOS 1, N1, and NMOS 2, N2. Both are NMOS. So what will happen if S is equal to 0? This is S equal to 0. If we apply 0 for the NMOS, is it on or off?
অফ।
Off. Right? So this is off. So B off means disconnected. Disconnected. So that means there is no connection between B and Z. Okay. However, S0 equal to S equal to 0, that means S bar equal to
ওয়ান স্যার।
1. Right? So if I apply 1 for NMOS, is it on or off?
অন
On. So that means transistor is on. So there will be a direct connection between A and Z. Does it make sense? All right. So let's see. Oh, here it is. That's a very good picture. All right. So let's see how. Here is the London Bridge. So this is terminal A. This is terminal Z. If we and this is the NMOS. If we apply 0, NMOS on or off?
অফ।
Off. Okay, that means disconnected. Disconnected. Now, left side is disconnected from the right side. Make sense?
জি স্যার।
Okay. So can you go through? Can you cross the bridge?
নো।
No. So when we apply, so let me say in one or two sentences. When we apply 0 for the NMOS, transistor is off. That means disconnected. That means signal cannot cross from one side to another side. Okay? Our summary is If we apply 0, transistor is off, no connection between left and right. So let me explain one more time. Is S equal to 0? This is S equal to 0. Is it on or off?
Off.
Off. That means disconnected. Disconnected. So signal cannot go from left to right. Disconnected. But S bar equal to 1 or 0?
1.
1. So that means connected. If it is connected, this is connected. So can you cross the bridge?
Yes, sir.
Okay. Now this is connected. So the signal can cross from A to Z. So as you can see, Z equal to 0. This is disconnected, no connection between B and Z. S bar equal to 1, connection between A and Z. So that is why Z equal to A. Make sense? No?
Yes, sir.
And similarly, S equal to 0, that means S equal to 1. So if S equal to 1, S bar equal to
0.
0. So it is disconnected. N1 is disconnected. So there is no connection between A and Z. S equal to 1. That means N2 on or off?
On.
On. So there will be connection. So that means B and Z are connected. Our signal can cross from B to Z. So that's why output Z equal to B. Make sense? No?
Yes, sir.
Okay. So this is a very simple example of 2 to 1 marks. And you can see it's all because of behavior. If I do this, then it will happen. If I do other thing, then something else will happen. This is purely behavior. Just like any other person, if you give me some money, I will be very happy. If I lose some money, I will be very sad. Okay, any question about if else? Although we are on the same slide for more than half an hour, but we learned few things in terms of circuit diagram. We learned about fast transistor and how the basic operation of fast transistor. And second thing, that if we have a fast transistor, output must be resisted because we need to hold the value. If we disconnect it, just like this one, this bridge. So if I disconnect between this side and that side, I don't know. I know input because that I applied the input. But I know because this is disconnected. I don't know what is on the other side. Okay? So that's why I need to save the value. If we disconnect a fast resistor, we need to save the value. That's why we have the resistor. Now we have behavioral model. Behavioral model will start with always and within the bracket we have to include the necessary input, necessary, not all, necessary input. So in this case, all the inputs are necessary, A, B, and S. If S equal to 0, because of the circuit operation, output will be connected with A. If S equal to 1, output will be connected with B. And then N1. All right, any question? All right, if not, let's move on. Okay. So we're going to analyze a few more examples based on 2 to 1. So here we have 4 bit 2 to 1 marks, 4 bit. Okay. If you recall that we had 1 bit full adder, then we had 4 bit full adder. So similar to that, here we have 4 bit full adder, 4 bit multiplexer, 4 bit 2 to 1 multiplexer. So that's why we have 4 multiplexers in parallel. This is bit 1, bit 2, bit 3, bit 4. And output is also bit 1, bit 2, bit 3, and bit 4. This is a very simple extension, very simple example. Module keyword, module name, input output port. Now, the only difference is A and B are both 4 bits. So bit 1, bit 2, bit 3, bit 4, 4 bits. I'm going to talk about it a little bit later. Output is also 4 bit. Y1, Y2, Y3, Y4. Oh, sorry, Y0, Y1, Y2, Y3. That's output. And also, because this is 2 to 1 marks, I have to save the data, output result. So that's why we have it registered. Only one difference. Only one of the signal is only 1 bit. That is S. Now, why S is a single? Because all the 2 to 1 marks operate in parallel. In parallel. Okay. So that means that we can use only one signal to control all 4 marks, so that we can get the output at the same time. Parallel means same time input, and it will appear at the output at the same time. if I use 4 bit selection, then it will run independently. Like I can change the value for this one sometime, then later on this one, and this one. I want the output at the same time. I need to apply the selection pin or selection bit at the same time. So if I apply the selection signal at the same time, I can just short circuit connect all the selection pins together. And I need only 1 bit or 1 signal to change the value of all the multiplexer. Does it make sense?
Yes, sir.
Okay. Other than that, everything remains same. Always add A or B or S. If S equal to 0, then output will be A. Oh, in this case, it's Z, right? Sorry, previous one was Z. But anyway, just change your variable. That should be okay. And else, output, if S equal to 1, output will be B. Okay. Hopefully, it makes sense. One small thing is that if you notice that A is 4 bit, B is also 4 bit. So, but here we have only A, B, and S. It means when we do not mention anything, it will consider as all 4 bits together. All 4 bits together. All 4 bits together. and also at the same time y equal to a. So which bit? Is it y0, y1, y2, y3? So it will be all together. That means when we write this equation, it is actually a combination of four signals. y equal to a means okay. Hopefully it makes sense, right? So it is just a shorthand. Rather than writing all four bits independently, I can write it in a shorthand altogether. Does it make sense? Okay. So what is the benefit of writing it as a shorthand? Because this is only 4 bits. I can have 32 bits. So I have to, if I have to write it independently or individually, then I have to write 32 lines. So that's really long, long code, and there will be, obviously, I will make some error. So in order to avoid that, and in order to make life easy, we can write it in a shorthand form. And similar to that, y equal to p. All right. Any questions? In order to explain S, let me see if I can find a good example to explain S. And I think I can think about it. That would be hmm. So here is an example. I'm sure you already learned about it in 284, 283. So here we have a clock. This clock is applied to all the JK flip-flop at the same time. So clock, clock, clock. Some similar to that. Every time we apply a clock pulse, it will count 1, 2, 3, 4. So similar to that, this selection will be connected. The same selection will be connected for all the multiplexer. Whenever we select 1 or 0, the output will change at the same time, parallel. So here is another parallel example. What happened? What is it? So every time we apply a clock pulse, output will increment, and the output will come out at the same time, synchronous, same time. Make sense? All right. I hope it makes sense. Do you have any question? Okay, let's move on. What is going on? Now we have little bit complex example. Here we have only 1 marks, but it is 4 to 1. 4 to 1. So how do we define this circuit? When we have 2 to 1, 2 inputs. Now 4 bit 2 to 1. 4 bit means parallel 4 bit. But individually it is 2 signals, A and B. And total number is 4 in parallel. So there are 2 numbers that is important. 4 means parallel. 2 to 1 means individual is 2 input, 1 output. And if it is a 4 bit or 8 bit, then the number of 2 to 1 marks will be total 4 or 8 or whatever. So we have to understand this numbering system. So here we have 1 bit. Again, 4 bit means 4 outputs. 2 means independently we have 2 inputs. Okay, I hope that makes sense. Now here we have 1 bit. That the output is 1 bit. Then 4 to 1. 4 means input, number of input 4. So I hope you understand the numbering format, or what means, or which number means what here. Any question? Any question? Okay, that's fine. Now we have 4 inputs and 1 output. So we need 2 bits selection pin or selection value, because in order to select 4 values, we need 2 digits number. 2 digits number will give us 4 combination. If from 1 bit only, right? Why 1 bit? Because we have 2 inputs. With the 1 bit, we can select 1 out of 2. Here we have 4 inputs. In order to select 1 of 4, I need 2 bits. 2 bits will give us 4 combinations. Okay. Now, if selection is 0, 0, output will be connected with X. Which one is now? X0. Selection is 0, 1. Output will be connected with X1. 0, 1, 0. Output will be connected with X2. 1, 1. Output will be connected with X3. So let us write a code for this multiplexer, for 1 multiplexer. Now, if we look at this diagram, I need to identify the input and output port. So inputs are X, output will be Z, selection will be S. Input, output, selection. So only 3 signals. Although we have 4 inputs, but total number of port will be 3 only. 3. So here is the interesting part. When we had 2 to 1 marks. We had 4 input output. Now, if we increase the number of inputs, the number of port will decrease. So there is a mismatch. So how can we solve this mismatch? Another way to write it, module so it is equivalent to right. So if I look at it, look at the circuit diagram. So this is the direct form x0, x1, x2, x3 like this. And we need 2 bits for S. So S0, S1, but output is Z or Y, whatever you provided. But here the code is a little bit different. We have group of X, group of S, and Y. So how can I how can I solve this mismatch? In order to solve it, I can combine x0, 1, 2, 3 as an array. Make sense? And y is just y. Okay, so this is how we can convert or make sure that we match uh, all the ports and signals together. All right. So X will be 4 bits, S will be 2 bits, output is only 1 bit because we have only one output. And because it's a mux, we have to save the data. We already know that a mux can be open circuit or disconnected. That's why we need to save it. Otherwise, the output will be unknown. Is it clear? This definition? I have this new tool. Is it clear? This definition? Can you see my red circle?
Yes, sir.
Yes.
I installed it this morning. Okay. Now, do you understand this part? Okay, good. Now, I don't know how to change the color, but I will run it sometime. Next part, always. Ooh, I like it. This is my new toy. Always add, as I mentioned earlier, I have to list the inputs. What are the inputs?
X.
X and S also.
Yes.
X. So here it goes 2 minutes. All right. So next line is if S is equal to 0, y will be, sorry, y or z, will be x0. Then x equal to 1, x equal to y equal to x1, etc. etc. Make sense?
Yes, sir.
Good. So now things are becoming very easy. So we are learning it step by step. Any question? Okay. All right. Natural extension is 4 bit, 4 to 1 marks. So 4 bit, 4 to 1 marks. What does it mean? Right. So there are 4 marks. That means 4 outputs. 4 bit means 4 output. And and each of the so um, so this is y1, sorry, 0, y3. Okay. Now each of the input across 4 means like this. Okay, make sense? Right. Right. So this is a very simple extension. All we need to do, look at this output. It's a shorthand writing. Can you turn off your mic? Okay. So this is, here we have input 4 bits. We also have input 4 bit. The only difference is output is 1 bit. Here the output will be 4 bit. So here is 1, 2, 3, 4 bits. Output is 4 bits. That's the only difference. Make sense? Oh, by the way, so this is written in 2001. As you can see, input, output, and signal are declared at the same time. All right. Is there any question?
স্যার আমরা কম্প্যারিজন সিম্বল ইউজ করছি কেন ইফ
Okay.
স্টেটের মধ্যে s ইকুয়াল টু
What so when we use a single equal, it's a assignment. That means left side of the equation, right side of the equation. And here we have comparison, like is it equal or not equal. So it's a logic, and it's a arithmetic operation. This is a logic operation.
স্যার তাহলে 2 to 1 মার্কসের ক্ষেত্রে আমরা যে শুধু s ইকুয়াল টু 0 ইউজ করেছিলাম
Mhm. Oh, I understand. So you can write 0 also. That's not a problem. So the signal will just change. Make sense?
so I can use any of the two
But
or both
right,
equal or single equal.
this is arithmetic operation. This is logical operation. double equal is logical operation, and single equal is arithmetic operation. Is it clear now?
জি স্যার।
Okay. All right. So I think we understand this one also. Now, next is this is just- hmm. So we are done with if-else statement. So we have learned many different combination, 2 to 1 marks, 4 bit 2 to 1 marks, 4 to 1 marks, 4 bit 4 to 1 marks, many other combination, and it can be any different combinations. Next, we are going to learn about case statement. Just like, have you? Is there any? I think there is some there is a common switch and case statement for C++, right? I don't think there is MATLAB code for switch, but in C++ we have switch and case statement. Do you remember? Oh, all right. So we are going to learn same thing one again, slightly different syntax. That's all. All right. So I think I've been talking for like 1 hour. So I'm going to take like 5 minutes break. Then we'll be back again. And today we are going to learn about case statement. That will be our last topic for today. So what time is it? 11:03. So we're going to back. We're going to come back at 11:08. All right. think we can start. Case statement is almost similar to if-else statement. So let's take a look at it. Again, we have 4 to 1 marks and also 4-bit 4 to 1. So the inputs will be X, S, and Y. X, S, and Z or Y. So inputs will be, here we have 4-bit inputs, selection bit, 2-bit selection bits. Output is 1-bit output, and that output is declared as the register. Always add list of inputs. So instead of if else, we can write case. Case S. That means we are going to check again. I think I deleted that. So something similar to this. Anyway, so it's going to keep checking the value of the parameter S. If there is any change of S, it will check the value of S. If S equal to 0, then output will be X0. S equal to 1, output will be X1. S equal to 2, output S2. S equal to 3, output S3. X3. Just like. So end case. So here we have if else. We have if else, but no end. No end if. We are going to write end module directly. But for the case, we have always case. This is the logic for the case. And then end case. We have to write one extra line. I don't know why they did it. But this is the syntax. And then at the end, the last line would be end module. Very simple. I'm sure everyone understood it. But if you have any question, let me know. So you can interpret this. I'm going to check S. If S equal to 0, this. If S equal to 1, this. If S equal to 2, this. If S equal to 3, this. Exactly, you can interpret it as an if else also, but with different syntax. That's all. Any question? Okay. All right. So we are going to go through some extended example. So we have this truth table, and it is called decoder. I think everyone knows about the decoder. It, multiplexer, many output, many input, one output. Decoder, uh, binary value, output will be uh, uh, decoded like 1, 2, 3, 4, 5, 6, just like that. And input is the binary. So here we have 2 to 4 decoder. 2 to 4 decoder. And this is the truth table. So in the truth table, I don't have the schematic, but we have the truth table. En is the one of the input, enable input, and A0, A1 are data input. So we have two types of input, enable input, data input. So I'm sure you already learned about it in 283. What is the enable input? Just like this selection, we can consider is the enable. Enable means it will work. So selection, if I make the selection 0, it will not work like this because it will be disconnected. So enable means everything is disconnected. Nothing will work. So enable is 0, 0. Then it does not matter which input we are going to provide. For any input, output will be always 0, 0, 0, 0, 0. But if we have enable, that means it is active. You can consider this first line. Suppose the battery is dead, so it is disabled, not enabled. So no matter what button you press, the screen will be always off. Now, if we have enable, then input will work 0, 0. Then Z0 will be 1, rest will be 0, etc. etc. Okay, so this is the truth table. So let's see how we can write a Verilog code. Initially, all the input output. Now, A, how many bits do we have for A? 2 bits, right? Enable 1 bit. Z
4 bits, sir.
4 bits, right? I think I have a typing mistake here. It should be Z, not W. Let me. Why do we have to have register here? Why the output is declared as a register?
Because we need the values from the prior. So it's মানে memory লাগবে আমাদের এখানে.
Right. So if you see, if there is any chance of disconnection or disconnected signal like enable, if we may apply 0, that means input and output will be disconnected. So as you can see, no matter what kind of input we are providing, output is always 0. So if there is any chance that the circuit will be disconnected, then we have to use the output as memory. Again, if you go back, there is a chance of disconnected input and output. Where is my breeze? So disconnected, left side disconnected from right side. Then I know input, but I don't know output. So output must be memory. So here we have similar situation. No matter what combination, if there is any chance of disconnect, input and output will be disconnected, then we have to use the output as memory. All right. Now, a behavioral model always add what are the inputs, list of input. Right. We don't write output in the always. Only necessary input. Okay. Now, how can we code it? I can use if, else, or case, or maybe combination of both. If enable equal to 0, if enable equal to 0, how output is absolutely 0. There is no chance that there is any other value. It will be exactly 0. If enable equal to 0, No matter what is the input, output will be directly 0. Alright, but if enable equal to not 0 or enable equal to 1, else, then we are going to check. I can write a lot more if, but we can write it in a, how do I say, in a structured fashion. Else, case A, we are going to check A. Okay, because enable 0 and else means enable 1, already done. Enable equal is done. Now we are going to check A. If A equal to 0, output will be 1 0 0 0, 1 0 0 0, and so on. And at the end, we have to write end case, then end model. Make sense? This, this is just a coding because of the truth table. Because of the truth table. Oh, I think I understand what you're saying. You said that Z3 must be here, right? Z3 must be MSB. River. Oh, I see. I see. Oh, no. That's the typing mistake. I think something happened for that. That's typing mistake. Right. Now it is fine. What is happening here? Hmm? Okay. All right. So definitely this was a syntax mistake. So I corrected it. Other than that, uh, whatever truth table we have to follow that one. Like we have 1 at the beginning, 1 0 0 0, 0 1 0 0, 0 1 0 0, just like that. So was it your question that why is it 0 to 3? Okay, all right. So that was my typing mistake. Any other question? All right, let's move on. What do I have here? Anyway. This is a little bit complex. Why I don't encourage you to do it. Something that you got right. The module section remains same. However, we can write it in a little bit alternate way. Always add an. Now here you cannot. We don't see if here, so we can write it a little bit alternate way, and that is uh, case enable a. Okay. So this symbol is called concatenation. That means combining two signals together. So combining two signals together means we have 0, then 0 0 0 1 0 0, etc., etc. Everything will be combined. Then 1 0 0. So 0 0 0, value 0 0 0 1 1 0 0 2. Oh, all right. And then instead of 1 2 3 4, if enable equal equal to 1, A 0 0, then Z will be this value. It's a shorthand writing. Now we have only four combination. What would happen if we have this combination? Then that is called the default value. The default value is always 0. Default value is always 0. Let me try to explain it. So how does it work? How does it work? Is, by the way, it becomes capital because of word. So it must be small case all the time. What does it mean? It means okay. 0 0 0 0 0 0 0. So this is the first one. I can write also 0 0 1. So since it is 0, output will be all 0. Now dot, 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 dot. But when we start 1 0 0, then it will be 1 0 0 0 0. Fine. And so on. Okay. Well, let's see how can we uh, explain these lines. Enable A. Enable A. If I consider from this value, I can write, you can see 1 0 0 1 0 0. For that case, Z will be 1 0 0 0. So enable, write it down, EN, it will be 3-bit value, binary value, and the value itself 1 0 0. Next one will be 3-bit value, 3-bit binary value, 1, 0, 1. And corresponding Z1, Z2, Z3 will be 1, 0, 0, 0. It's a 4-bit binary value, 1, 0, 0, 0. What will be the next one? Next output? Can you tell me? So enable combining with A will become enable combined with A will become 101. So here's 101. Combining all the Z will be 0, 1, 0, 0.
0, 0.
And so on. I hope you understand. All right. Now I can write next two cases also. Okay. So here are all the 4 values.
স্যার এখানে enable এটা 100 হবে না যদি ও
Which one?
আচ্ছা enable সহ কাউন্ট করব 110টা
110. This one?
হ্যাঁ হ্যাঁ মানে enable এরটা 1
Right.
তারপর A1 এরটা তারপর A0 এরটা
Right. So enabling is 1 bit and then 2 bits. Total 3 bits.
Hmm.
Also, or I can write okay.
Yes.
Oh, all right. But now we have already considered all these 4 values. But what will happen for the other 4 values? Other 4 values. Other 4 values, I can write it in one single line. Single line. Because it's in the truth table, it's only one single line, right? So that's why I can write that in one single line, which we'll call default value, because we are grouping or combining multiple outputs in one line. That's why we call it default value. If this 4 value does not match, then it will be default value, and that default value will be actually default, and the default value is always uh, we can write this way, or we can write just simple 0, because our default number system is decimal. As you can see, default Z equal to just 0. I don't have to write all the bits, only 0. All right. And at the end, we have to write end case. Make sense? Okay. All right. If there is no other question, let's move forward. So we're going to do an example, and you'll see it'll be very easy. Just a uh, larger code or long code. That's it. Because a little bit more parameters. Anyway, so we have this BCD to 7 segment display. Everyone knows about it. Uh, Not many people use it anymore because now you're using LCD display, etc., etc. But these are one of the classic display system or display board people used to use. So let's write a code, a Verilog code, so we can display 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It is called segment display because there are total 7 LED, A, B, C, D, E, F, and G. Total 7. So by turning it on and off, we can display different digits. Here is the BCD 7 segment. The ports, input, output. So here is the logic diagram. Input, output, all the ports. Now, 7 segment BCD, binary coded decimal. So how many bits do we need in order to represent 0 to 9?
4 bits.
4 bits. Although 4 bits is more than that we need, but for binary we can only have 2, 4, 8, and 16. So total width for BCD or decimal coded, we need 10 digits, so more than 8. So we have to jump to 16. And for 16 bit, we need, for 16 values, we need 4 bits. So that is why BCD is 4 bit. 7 segment display. How many bits do we need from the truth table? 1, 2, 3, 4, 5, 6, 7. 7. 10? No,
Yeah,
not 10.
same.
7. So because there are 7 outputs, 7 display. So that's why we need 7 digits, A, B, C, D, and G. So that's why we have 0 to 6. I don't know what is going on here. But, right, again, why LED is registered?
যখন জিরো থাকবে তখন তো মেমোরি থেকে ভ্যালুটা নিতে হবে।
And not necessary. Memory is correct, that's fine. Because suppose if we disconnect
ও
the
আচ্ছা,
input and output, then we need to save the previous value. Otherwise, if we do not save it, it will turn off, right? If I disconnect it. But suppose we have, I think we still have LCD LED display. In different shops, they have this banner and etc. etc. Sometimes some of the banners are they keep it on for 20, I mean for long hours. If they keep it on for long hours, and if they always need to provide the input, then there will be some power loss and etc. So they disconnect the input, only keep the output, so they can minimize the power loss. But in order to keep the output, I need to have the memory. So that is why we define it as a register. Behavioral modeling. Always add. And how many input lists we are going to have, or how many inputs that we're going to have in the always? What do we include in the always?
BCD value গুলা.
But so what is the general logic or general syntax? Inside always, what do we include?
Necessary input.
Inputs, only necessary input, correct? And in this case, these are simple example. Necessary input, we have only one input that must be necessary. Anyway, now case, if 0, 0, 0, 0, 0, then LED will be this pattern, this pattern, this pattern, this pattern, this pattern. But as we know, we have 4 bits. We can have 16 combination, but after 9, I don't have anything, right? Can we have 10? Because it's only one digit, 0 to 9. This is 10. What I'm going to do with it? Then we can have don't care, we can have any other value, but in this truth table we're using don't care. So don't care means XXXX, don't care. So from 0 to 9, 0 to 9, we have the pattern, but after 9, don't care. From 10 to 15, don't care. Then end case, end module. Very simple. Is it clear for everyone? All right, very good. Okay, let's see what we have next. So we already did if else case. So here we already did if else case. Since we are here, I'm going to take 5 more minutes. Then I'm going to end it. So one of the operator that we use for shorthand is called conditional operator. Condition means what? If. So this is the shorthand for if statement. We have a question mark, we have a colon. If A is true, output is B. If A is false, output is output is C. So let me provide you some examples. These are all good. 2 to 1 marks, input 1, input 2, selection and Y. You understand this? 1 bit input 0, 1 bit input 1, selection is 1 bit, output is also 1 bit. We can do it data flow, we can do it behavior, we can do it structural. So here we are using the example for data flow. So data flow means assign output Y is equal to, if selection is 1, output is in 1. If selection is 0, output is in 0. So just like that, selection 1, then output in 1, selection 0, output in 0, in 1. So this is a shorthand for if else. In the behavioral modeling, we use if else. We can use the same thing for data flow, but for data flow, if else, the symbol for if else will be question mark colon. We have few other examples. So now we have array and etc. Lots of complexity. So we have 4-bit inputs. If we need 4-bit input, then we need to have 2 bits selection, and output will be always also 4-bit. Now, if S1 equal to 1, then it will check S0. If S0 equal to 1, then output will be D. Otherwise, output C. So I think we also did nested operation. So one if inside another if. Now, if S1 equal to 0, then it will check S0. It will be either output B or A. So here is the interpretation or if else format. If S equal to 1, then it's gonna check another if S0 equal to 1, then output D. But if S0 equal to 0, output will become C. Now next one, if S1 equal to 0, if you can write else or whatever you prefer. Then it will check again S0. If S0 equal to 1, then output D. S0 equal to 0, output will be A. I can make one more internal if else, again internal if else. I can make it 100 levels, 400 level, 500 level, or 500 if inside another if. So there is no stopping. Obviously, it will become very complex, but at least you know it. So this is the shorthand if else for data flow statement. Any question? Okay. So I think I'm going to stop here today. So we learned especially the behavioral modeling in terms of if else, in terms of case statement, and one of the most important thing is for the pass transistor or in general, if there is any possibility that output will be disconnected from the input, then we have to use resistor. And we checked quite a few examples. But if you still have any question, let me know. Otherwise, we're going to end this session for today. Okay. Now and then, I think if there is no question, so we can end this session. So if anyone recorded this session, you can send me a link. I will upload this recording in the Google Classroom. Okay, send me the link. All right, so that's it for today. If there is no question, so I'm going to end this call. All right then, so we are going to meet next Friday. I'm going to post another notice, either Thursday or Friday. Oh, sorry, Thursday. But it will be saying link and etc. But anyway, I'm going to send all the information before Friday for another online class. Okay, so I'm going to end this call now.